In this video, we will explore proof by induction. As you can see in the cover here, we're going to try to prove that 5 to the power of 2n plus 11 is always divisible by 12. Now, what is proof by induction? In order to get to that, I'd like to motivate you by showing you why you might need such an idea. So let's take a look and if we can try to prove this without any induction. So here I'll make a table of values for values of n and then evaluating 5 to the 2n plus 11. When n equals 1, we get 5 to the 2 times 1 plus 11, which simplifies to 5 squared plus 11, or 36. And indeed, 36 is divisible by 12. It is 3 times 12. Okay, let's try that with another value of n. How about n equals 2? In this case, when you do that, you get another multiple of 12. It's 636, and that's 53 times 12. We could go again and try that with 3, and you'll see again the answer is a multiple of 12. But really, do we want to sit there and go forever to prove that it's always a multiple of 12 for any value of n? Well, that's not going to really become a proof because it's going to go on forever, and you really will never be able to show every possibility. Hence, we want to introduce a proof maybe of some other sort, which we're going to call induction. What is a proof by induction? Well, a proof by induction consists of 3 steps. First, you want to show that it's true for n equals 1. That's kind of the base case. Then, you assume that it is true for some natural number k. So you assume that it's true for n equals k. Then, the third part is to prove that it's true for k plus 1. So if you prove the third one, you'll end up with a sequence that's unbroken from n equals 1 to infinity. And that's the idea here. To prove by induction is to create this chain reaction. So, step number 1. Let's prove it's true for n equals 1. Okay, so we actually did this earlier in the table of values that I provided at the beginning. See, you put 1 in for n, you simplify a little bit, and you get 36. And 36 is indeed a multiple of 12. Hence, step 1 is complete. Now to step 2. We assume that it is true for n equals k. So, we let n equal k, and we assume that this expression is divisible by 12. So, we can write it differently as 5 to the 2k plus 11 is 12 times some other number q, where q is a positive integer. So z plus there means positive integers. So we're going to use this important step to clarify our proof for step 3. Now we're going to prove that it is true for n equals k plus 1. So we want to see that this expression here, when we substitute k plus 1 for n, will be indeed divisible by 12. So substitute in k plus 1 for n, and you get this expression here. And you can use some exponent laws here. Here we distribute the 2 into the brackets. Now we can separate using the exponent law for addition of exponents. Notice that 5 squared is 25. Interesting enough here, it looks like it's not, I don't see an obvious 12, but you can do this trick here in red, which is to add and subtract these 2 terms, which will allow us to do a grouping step shortly. So what I've done here is I've grouped it into the yellow and the green terms. Notice that the green terms have a factor of 11. You can calculate the difference of 25 and 1. So I just move that over here to the side. This is the longest step, obviously. Step 3 is the long step in the induction proofs. So there you go. Now we can simplify a little bit further. And notice in that bracket, 5 to the 2k plus 11, wait a second. That 5 to the 2k plus 11 is what I mentioned earlier. That's our second step, which was to assume that it is indeed a multiple of 12. So now you have 2 terms that are multiples of 12 because they have factors that include 12. So let's take out that 12. So you see, our original expression evaluated at k plus 1 now equals 12 times a number. That's it. We have indeed demonstrated that 5 to the 2n plus 11 is indeed 12 times a number, or a multiple of 12. Hence, we have completed the unbroken chain of values of k from 1 to infinity for the proof by induction. We summarize here the proof by induction, 3 steps to glory. If you like what I've showed you here, please subscribe to the channel. Also, I'd like to mention that if there are math questions that you'd like to see answered that are a little bit out there, I don't mind, and the level doesn't matter. It could be really old or really young. You could be doing a master's or a PhD, or you could be doing something in grade 6. I don't care. I love to show you and share my ideas with you. Thank you very much.